This is problem 77, chapter 8 of Giancoli 6th edition. So we have a hollow cylinder, a hoop, that is rolling on a horizontal surface. So if it's a hoop, the moment of inertia is given by the mass and the radius squared. Okay? And they give us the initial speed of the hoop. So it's moving on this horizontal surface until it reaches an incline. And we know also the angle of this incline. So this is what is going on. We have this hoop moving and it will find this incline. What we want to know is how far up the incline will it go. So how far up means this delta x here. Okay, so this is the unknown on this problem. To find this delta x, what we need to find is the height. With the height, with the angle, I can find this delta x. So to find the height, I'm going to use conservation of energy. So for part A, I'm going to use conservation of mechanical energy. Initially, the object has only kinetic energy, but remember it has both translational kinetic energy and also rotational kinetic energy. So we have here 1/2 of mv squared and also 1/2 of the moment of inertia and omega squared. At the end, the object will stop, it will reach the maximum height, will stop, and it will have only gravitational potential energy. Okay, now mass is not given to us, but do not worry because you'll see that it will cancel. If we write the moment of inertia as mr squared, you see that the masses will cancel. Let's also write this angular velocity as v divided by r. Okay, so this equation now is 1/2 of mv squared plus 1/2 of mr squared v squared over r squared equals to mgh. So you see that the masses will cancel. And also the r, the radius was not given, but it also cancels. So from here we can find that height. So that height is given is v squared divided by g. Remember, this is not the answer of the problem. We still need to find delta x. So how are we going to do that? We use that triangle. We know that the sine of that angle is the opposite, the height, divided by the hypotenuse, which is that whole delta x. So from here, we can find our delta x, which is just equal to that height divided by the sine of theta. And so don't get confused. This letter h here is for the height. Okay, so this letter h here is for the height. Okay, we are done with part A. We go now for part B. Part B is asking how long will the hoop be on the incline before it arrives back at the bottom. So careful with what they are asking us here. So for this part B, what we have is the hoop starts at the bottom of the incline, goes up, but then it comes back down. So they want this whole time to go up and then down. What I'm going to start from is the time to go up, and then we know that we'll just have to multiply by 2. To find this time, I'm going to use that equation from chapter 2 that involves the velocity, because I know that at the top the velocity will be 0. So I'm going to write it like this. V is equal to the initial velocity plus at. Okay? This initial we know, the final at maximum height will be 0. So everything looks good, except that I do not have this acceleration. Well, how can I find this acceleration? I could use, for example, this equation. No? V squared is equal to V naught squared plus 2a delta x. Everything here we do have. We know that at the end, at maximum height, we have 0 velocity. We know the initial, and we know the delta x that we just computed on the top, so we can find the acceleration. With the acceleration, we can come here and find the time, but remember this is just the time to go up, so the total time the total time is twice the value. And that's the end of the problem.